So since your arrows are pointing in the negative f of x direction, so negative infinity, you have your two arrows in two different regions with your x. You have one arrow, which is the left arrow, that is in the negative x region. So you know this arrow on the left is going to keep getting wider and towards the negative infinity of your x region as it continues to grow in the y region in the negative direction. And then this arrow right here is in the positive infinity for your x region. So in this case, your degree is even, so you know your arrows are pointing in the same direction. Since it's negative, you know they're going to be pointing down. So the only option for your y is that it's going to only approach negative infinity, and then you have two different arrows in two different regions of your x. You have a negative x region for the first arrow, the positive x region for your second arrow. The next two scenarios for your polynomial functions are if we deal with your degree that's odd. So in this particular case, if you have an odd degree with a leading coefficient that is positive, we're going to talk about that over here, and then if you have an odd degree with a leading coefficient that's negative. So again, we're going to give you two really simple examples to look at. The first is x cubed. So if I kind of graphed x cubed, I'm just going to sketch this so it's not going to be very accurate, but it's going to look something similar to this if it was your parent function. So you have your f of x, which is your fancy for your y, and then your x-axis. Now in this case, I'm going to still circle both of my arrows. Now what's different with an odd degree is that you have two arrows going in the different direction. Where your even degree, both your arrows are pointing in the same direction. So since your arrows are in opposite directions, your f of x, you're going to have two different scenarios for f of x, where in the above two scenarios, you only had one option. So the first is we're going to start with the lower arrow. We're going to read left to right. This arrow down here is pointing down. So in the first case, f of x with this particular arrow is approaching negative infinity because it's pointing down. As x approaches, well, since this arrow is in the negative x region, it's going to be approaching negative infinity. And if we go to this arrow over on the right, it's pointing upwards. So here f of x is, for this particular arrow, this end behavior, as f of x approaches positive infinity, it's going to continue to grow in the positive x region. So your x is going to get bigger and bigger in the positive x infinity region. So again, odd degree, your arrows are going to be pointing in opposite directions, but again, if you connect them, you're going to have a positive slope. So that should match the fact that you have a leading coefficient that's positive. In the last scenario, we're dealing with a degree that's odd, but your leading coefficient is negative. So you have a negative x to the 5th power. And I'm going to just kind of sketch. This is not very accurate, but it's going to look something similar to this. And in this particular case, if I circle both arrows, f of x is my y-axis, x is my horizontal x-axis. So now in this case, as f of x approaches positive infinity, because it's pointing upwards towards your y, my x is going to be, or my arrow is going to be in my negative x region. And I have my other arrow for the end behavior. If this continues to grow, my f of x, and now in this case it's pointing down, so I'm getting negative infinity as I'm growing, but I'm in the positive infinity x region. So those are your 4 scenarios when we're talking about end behavior. It tells you over a lengthy period of time, or if that continues to grow, your graph continues to grow, what will happen as those arrows continue to get bigger and bigger and bigger. So let's jump to example 1, where we're going to start dealing with the graphs of these functions. And from the graph, describing what the end behavior is. So starting out, we're given, right off the bat, the polynomial function negative x cubed minus x squared plus 2x. The first thing I notice is that it's in standard form because I'm going in descending order with my exponents. So I'm already in standard form. So I can actually fill this part of my letter A of the problem out already because I already know my degree, which is 3. So I know it's going to be a cubic function, that's the type, and my leading coefficient is -1. two things I need to pull from this is the first is to notice that 3 is actually an odd number. That's really the most important part. 3 is an odd number. And my leading coefficient is negative. So from my degree and my leading coefficient, because I can find this in standard form, if it wasn't in standard form, I'd have to write it in standard form first. I can actually assume what my graph is going to look like because it's one of the types we just talked about. Odd means your arrows are going to be in opposite directions, and it's negative. So if I had to guess, and I'm just going to graph it out, it's going to look something along the lines of this with a squiggle, where if you connect your two arrows, you're going to have a negative slope. So let's graph this equation and see if it actually is a little close to my little sketch and what I'm expecting it to be. Once I know and I can graph, I can then fill out my end behavior. So the first thing I'm going to do is I'm actually going to plug in numbers, okay? So if I'm dealing with this guy right here, it tells me what my domain is. They already tell me what to use for my x values. So I'm going to plug that domain in on the left side of my table. And if I plug -3 into this equation, I get -3 cubed minus -3 squared plus 2 times -3. So if I crunch those numbers either in my head or in my calculator, I should get 12 as my y value. If I plug -2 all the way in, I get -2 cubed minus -2 squared plus 2 times -2. If I crunch that into my calculator, I'm going to get a -8, so I get a +8 actually here. I get a +8 minus 4, because this ends up being a +4, so -4 plus, and this ends up giving me a -4. So if I plug all that in, I should get 0 for that value. So if I continue to plug them in, you guys are going to, on your own, you can fill that in. You can even pause the video right now to plug these into the calculator and then restart the video up and make sure they match up. I'm going to give you the answers, but make sure you know how to plug them in. So if I plug -1 in, I should get -2 back out. If I plug 0 in, I should get 0 back out. If I plug 1 in, I should get 0 back out. If I plug 2 in, I should get -8. If I plug 3, I should get -30. Okay? And these are basically just ordered pairs. -3, 12 is a point I need to plot on my graph. So I get my x-axis, my f of x, which is just fancy for my y, and if I plot all of these points, -2, 0, -1, -2, 0, 0, 1, 0, 2, -8, and 3, -30. So let's plot those points. 3 over, so I get 1, 2, 3. 12 up would be somewhere way up there. -2 over 0 is right about there. -1, -2, 0, 0, 2, or 1, 0, 2, -8, and then obviously 3, -30 is way, way lower. So if I connect these dots, the dots tell you a little bit about what this graph is going to look like. So it comes back up and back down again. So if I connect those points, I'm going to circle my end corners, my arrows. It tells me about my end behavior. So the first is, I want to recognize that what I actually graph and what I expected it to look like are pretty similar, right? My arrows are going in the same direction. So starting from my left, moving over to my right, this f of x is going in the positive direction. So as f of x approaches positive infinity, I'm in the negative x region. So that's my first one. And I actually have to add more to this because I have another arrow going in the opposite direction. So I still have to fill in f of x approaches something as x approaches something. So let's figure out what that something is. So as f of x approaches, in this case, the other arrow, negative infinity, because I'm going down, my arrow is pointing downward. F of x approaches negative infinity as, and you have the arrow in the positive x region. So that's your end behavior for your example 1, letter A. So let's move on to letter B. Letter B is a different scenario. We have still our function is given to us in standard form. We go from a higher exponent and we're in descending order, so we know that we're in standard form. So the first is my degree is 4, which is obviously quartic. But more importantly, why do I care? Is because I know it's an even exponent, or even degree. My leading coefficient in this case is 1, which is a positive leading coefficient. So if I had to guess just right off the bat, because they're even, my arrows are going to be pointing in the same direction. Since it's positive, I'm going to assume that they're both going to point upward. Now, it doesn't necessarily mean it's going to look like a parabola. It just means that both my arrows are going to be pointing up and in the same direction. So let's plug in some numbers. Still, my domain is -3 to +3. So we start off with the smallest number first. 1, 2, and 3. And we plug them into our equation. So I get -3 to the 4th power minus 4 times -3 minus 1. And if I crunch those numbers, I get 92. Doing the same thing for -2, -2 to the 4th power minus 4 times -2 minus 1. I can crunch those in my head or on your calculator. That number should be 23. Again, you can pause the video at this point and fill in the rest of the work because you're going to need to have work here shown for credit. So make sure you pause the video and you guys can figure out and show the work for the rest of these values. But as of right now, I'm just going to fill them in for you. So if I plug in -1, I should get 4. If I plug in 0, I should get, let's see, -1. If I plug in 1, I should get -4. If I plug in 2, I should get 7. And if I plug in 3, I should get 68. So if I take those values, now these ordered pairs, -3, 92. -2, 23, -1, 4, 0, -1, 1, -4, 2, 7, and 3, 68. Obviously these endpoints, these further out points, I'm not going to be able to graph on my coordinate plane on the paper, but I can kind of estimate it as I sketch my graph. So if I plug those points in, f of x is my y-axis, there's my x-axis. So the one that probably is going to fit the most, I'm going to do -2, 23 is going to be really high up, so I'm just going to estimate up there. But if I go -1, +4, 1, 2, 3, 4, 0, -1, 1, 1, 2, 3, 4, and then 3 is kind of off the chart. Actually, 1, -4, 2, 7, 1, 2, so kind of hard to see, 1, 2, 3, 4, 7, and then obviously 3, 1, 2, 3 is going to be way off the chart. So if I connect these points, they kind of go through, they divvy down, and they come right back up again. But the idea, even though it doesn't look like a complete parabola, which it shouldn't because it's a different type of graph than a quadratic, regardless, you still have your two arrows pointing in the same direction, and they're both pointing upward, which is what I would kind of estimate or guess it would be just given my degree and leading coefficient. So right off the bat, I know that because both of my arrows are pointing upward, I only have one option for f of x, right? Because both arrows are pointing in the positive direction. So f of x can only continue to grow in the positive infinity direction. But I have two values for x. My first arrow is in my negative x region, and I also have an arrow that is in my positive x region. So f of x only has one option, and it's positive infinity. Where my x's, I have two different arrows in both the negative infinity x region and the positive infinity x region. So those arrows are going to grow in that direction, that way over time. So at this point, you have 3 Now You Tries that is part of your note-taking packet. So you guys can work on those Now You Tries and bring them to class the next time we meet formally, and we can go over any questions that you may have as well as the answers to the rest of this packet.